All right, get ready because we're diving into one of the most incredible books, Stephen Hawking's A Brief History of Time. Yeah, this book, it tackles like the biggest questions we've ever asked.
Absolutely.
Like, how did the universe even begin? What are black holes?
But could we, time travel? Is that even possible?
It's mind-blowing.
And you know a book is a total hit when it outsells, wait for it, Madonna.
What?
I know. Different subjects, obviously.
Very different subject.
But both iconic in their own ways.
Totally.
Yeah.
So in this deep dive, we're going to journey through like the highlights of cosmology.
That's right.
We'll start with the earliest ideas about the universe and go all the way to those super complex modern theories.
We're going to be talking about black holes that aren't even really black. Imagine the universe as this giant four-dimensional puzzle, and we'll even try to figure out the whole time travel paradox thing.
Oh, yeah, that's going to be fun.
It's going to be wild.
So Hawking, he starts the book with this funny story about the Earth, right?
Hmm.
And it's sitting on the back of a giant tortoise.
A giant tortoise, yeah.
But then, okay, so what's the tortoise standing on?
Well, on another tortoise, of course.
Of course. And it just keeps going, like forever.
Forever and ever.
It's such a funny way to show how people have always tried to explain, like, what the universe is built on, you know? Like, what's at the very bottom of it all?
Totally. It's like this deep human need to find answers, right? To understand where everything begins and if it even ends at all, you know?
Yeah, that's the big question. And the ancient Greeks, they took a shot at it.
Oh, they did.
With some pretty elaborate models
Live in
of
the
the
kitchen.
cosmos. They were trying to figure it all out.
So for centuries, the model everyone accepted was this Earth-centered one by Ptolemy.
Ptolemy, yeah.
And it's really complex.
Oh, it's so complicated.
Like all the planets, they move on these crystal spheres and they're all nested inside each other.
Crystal spheres, can you imagine? And, you know, part of why this model stuck around for so long, it conveniently left space for heaven and hell outside the outermost sphere. Oh, wow. So it fit in with what people believed at the time.
Exactly. Nice and tidy.
Very convenient.
A theological fit.
But then, in the 16th century, Copernicus comes along and just shakes everything up.
He really did.
He says, nope, it's the sun at the center.
Sun-centered model, boom.
A simpler model.
Way simpler.
But, you know, people didn't jump on board right away.
Oh, no. It takes time to change everyone's minds about something so huge, you know? Like how the whole universe is structured. It's a big deal.
It's like shifting your whole worldview.
Exactly.
And it's amazing how these early models, even if they weren't totally accurate, really shaped how people saw themselves in the universe.
Oh, absolutely. Their place in the grand scheme of things.
Yeah, like where do we fit in?
The big questions.
But then things changed drastically. We're talking about a massive shift from Newton's ideas to Einstein's theories.
Huge shift.
Newton, he gave us this idea of absolute time and space.
Yeah, like a fixed framework for the entire universe.
It worked really well for a long time.
It did, but then the speed of light comes into the picture.
Ah, yeah, the speed of light.
And things get, well, a lot more interesting and a lot weirder.
Definitely weirder. So you're talking about the famous Michelson-Morley experiment in the late 1800s.
The one and only.
They were trying to find this mysterious ether.
Yeah, the ether. They thought it was like the stuff that light waves traveled through, you know?
Right, like sound waves need air to travel.
Exactly.
But their experiment, it came up empty,
Nothing. No ether.
which basically threw the world of physics into a crisis.
A major crisis. Because if there's no ether, how does light travel through space? Space is a vacuum, right?
Right, empty space.
It was a big problem.
And that's when Einstein comes in
Einstein to the rescue.
with his theory of relativity.
Boom. Changes everything.
He just rewrote the rules.
Completely. No more ether. Instead, he says the speed of light is constant for everyone, no matter how they're moving.
Wow, that's a big one.
It is. It sounds simple, but it has huge consequences.
Like what?
Like, we can't think of space and time as separate anymore. We have to combine them into this crazy concept called space-time.
Space-time. Okay, how do we even begin to imagine a four-dimensional space? My brain hurts already.
I know, right? It's a challenge.
It's a lot.
But Hawking, he uses this great analogy to help us visualize it. Imagine you're drawing the paths of the sun and Alpha Centauri.
Alpha Centauri, the closest star to us.
Yep, that's the one. So you're drawing their paths through this 4D space. Light takes about 4 years to travel between them, so those points in space-time, they're not just separated by distance, but also by time. It's wild.
So it's like a map, but a map that includes time.
Exactly. A cosmic map where each point is a specific place at a specific moment. Pretty cool, huh?
So everything we see in the universe, those distant stars, galaxies. We're actually looking into the past.
You got it. The further away something is, the further back in time we're seeing it. It's like looking at a baby picture of the universe.
That's incredible. And to make things even more interesting, general relativity tells us that massive objects actually warp space-time.
Warp it.
Warp it. Like, imagine putting a bowling ball on a trampoline. The ball makes a dip, right? That curves the fabric of the trampoline.
I see where you're going with this.
Stars and planets do the same thing to space-time. They warp it.
So light doesn't just travel through space. It travels through this curved, warped space-time. Mind-blowing.
Exactly. And that means its path bends as it passes by those massive objects.
That's right. It's called gravitational lensing, and we've actually observed it during solar eclipses. Just like Einstein predicted, it was a huge win for his theory.
So Einstein was right. All right, now let's talk about the Big Bang.
The Big Bang, the granddaddy of them all.
It's the leading theory about how the universe began, right?
It is.
So the idea is that the universe started out super small, super hot, and super dense.
Like unimaginably small, hot, and dense.
And it's been expanding and cooling ever since.
And we have evidence for this. One piece is the redshifting of light from distant galaxies. Have you ever noticed how a siren sounds higher pitched when an ambulance is coming towards you and lower pitched as it goes away?
Oh yeah, the Doppler effect.
Exactly. It's the same with light waves. As galaxies move away from us, their light waves get stretched out, shifting towards the red end of the spectrum.
So that redshift is like a fingerprint telling us that the universe is expanding.
Precisely. And there's another piece of evidence, maybe even more convincing. The cosmic microwave background radiation.
Okay, what's that?
It's like the faint afterglow of the Big Bang, this leftover heat from the very beginning of the universe.
And this was discovered totally by accident.
Total accident. These two guys, Arno Penzias and Robert Wilson, they were just trying to get rid of noise in their giant antenna, and they stumbled upon this cosmic echo.
Talk about a lucky break.
Right. It was a huge discovery that really solidified the Big Bang Theory. It gave us a glimpse into the universe's Beatty pictures.
It's amazing how those accidental discoveries can sometimes lead to the biggest breakthroughs.
It's true. Sometimes the universe just throws you a bone, you know? But to understand what happened in those first moments, we need to zoom way in to the tiny, tiny world of quantum mechanics.
Okay, here's where things get really strange.
Buckle up.
We're talking about the theory that governs how atoms and subatomic particles behave.
It's a whole different set of rules down there.
And it's a world where things don't act the way we expect them to in our everyday lives.
Not at all. It's like Alice in Wonderland down there. One of the key ideas is that light can act like a wave and a particle. It's called wave-particle duality.
So light has a split personality.
You could say that. It's like it can't decide what it wants to be. And then there's the Heisenberg uncertainty principle.
Okay, this one really messes with my head.
I know, right? It's mind-bending. It says you can't know both the particle's position and its momentum perfectly at the same time.
So there's a limit to what we can know about the universe at that tiny scale.
Exactly. It's like the universe is hiding its secrets from us. And if you try to apply this principle to the very early universe, right after the Big Bang, things get even weirder.
Weirder than light acting like both a wave and a particle. I'm almost afraid to ask, but what happens?
Well, right after the Big Bang, particles were so energetic they were zipping around like crazy. It was pure chaos.
Chaos.
Pure chaos. The universe was like a giant particle mosh pit. Things were way too energetic for anything to settle down and form.
So it was like a cosmic dance party gone wild.
Exactly. But as the universe expanded, it also cooled down. Imagine those particles slowing down like dancers getting tired after a long night.
They needed a break after all that chaos.
They did. And eventually things calmed down enough for those particles to start sticking together. That's when things really started to get interesting.
So as the universe cooled, particles could finally form atoms and then molecules. And from there, it's a long but incredible journey to stars, galaxies, planets, and eventually, us.
We're all made of stardust, baby. It's pretty amazing to think that everything we see around us, everything we are, came from that primordial soup of particles.
It's truly mind-boggling. Speaking of mind-boggling objects, let's talk about black holes.
Black holes, those enigmatic beasts of the cosmos.
Black holes are those mysterious objects with gravity so strong that nothing, not even light, can escape, right?
That's right. Once you cross the event horizon, the point of no return, you're not coming back. It's like a one-way ticket to oblivion.
Hawking paints a pretty vivid picture of what might happen if you were to fall into one. And let's just say it doesn't sound like a fun experience.
Definitely not a trip I'd recommend. But what's fascinating about black holes is that they're not just these cosmic vacuum cleaners sucking everything in. They actually have a deep connection to thermodynamics.
Wait, black holes and thermodynamics, those seem like totally different realms. How are they connected?
Well, black holes have something called entropy, which is a measure of disorder. And just like the entropy of the universe is always increasing, the entropy of a black hole increases as it swallows more matter.
So as a black hole devours stars and gas clouds, it's actually getting messier and more disordered.
That's the idea. And this led to one of Hawking's most groundbreaking discoveries, Hawking radiation.
Wait, what? Black holes can radiate. How does that even work?
It's all thanks to those quirky quantum effects we were talking about earlier. Near the event horizon of a black hole, pairs of virtual particles can pop into existence.
Right, those virtual particles that pop in and out of existence. They're always causing trouble.
They are. But near a black hole, something strange can happen. One particle might fall into the black hole while the other escapes, and the escaping particle carries away some energy from the black hole, and that's what we detect as Hawking radiation.
So over incredibly long periods, black holes slowly evaporate due to this Hawking radiation.
Yeah.
It's like they're slowly leaking energy back into the universe.
Precisely. It's an amazing example of how Hawking brought together seemingly disparate areas of physics, general relativity, quantum mechanics, and thermodynamics to make a revolutionary discovery.
It really highlights his incredible insight and ability to see connections that others missed. Now, let's tackle one of the biggest mysteries of all, the very beginning of the universe. Classical physics, the physics of Newton and Einstein, breaks down at the Big Bang singularity.
Right. At the moment of the Big Bang, the universe was infinitely dense and hot. Our current theories just can't describe what happened at that point.
So how do we even begin to understand something as mind-boggling as the singularity?
Hawking proposed a radical idea called the no-boundary condition. It's a way to imagine the universe without a beginning point. Think of the universe like the surface of a sphere.
Okay, I'm picturing a globe. It's finite, it has a limited surface area, but it doesn't have an edge or a starting point.
Exactly. The no-boundary proposal suggests that the universe is finite but unbounded, just like the surface of a sphere. It's a mind-bending concept, but it eliminates the need for a singularity, a point where the laws of physics break down.
And this has some profound implications for our understanding of time. If the universe has no beginning, does that mean time itself has no beginning?
That's one of the intriguing possibilities. Perhaps time is also finite, but unbounded, like another dimension of space. It challenges our linear view of time, where we imagine it as a straight line extending infinitely in both directions. Instead, time might be more like a loop or a closed curve.
Okay, that's a lot to wrap my head around. But it's fascinating to consider how our perception of time might be completely wrong. And speaking of time, let's talk about the arrow of time. We experience time as flowing in one direction, from the past to the future. Why is that?
It's a fundamental question that has puzzled physicists and philosophers for centuries. There's this concept of the arrow of time, which describes this directionality. And it turns out there are different types of arrows of time.
Like the psychological arrow of time. That's the way we experience time subjectively. We remember the past, but we can't predict the future.
Exactly. And the psychological arrow of time is connected to the thermodynamic arrow of time, which is related to entropy, that measure of disorder we talked about earlier.
So, as entropy increases, time marches forward. But why does entropy increase in the first place?
That's where the no-boundary proposal comes in again. It suggests that the universe began in a state of very low entropy, a very ordered state. And since then, entropy has been steadily increasing, driving the arrow of time forward.
So the Big Bang not only set the universe in motion, but it also set the direction for the arrow of time. That's pretty incredible.
It is. It's like the universe started with a perfectly arranged deck of cards, and we've been shuffling them ever since, creating more and more disorder.
Now for the fun part, let's talk about time travel. It's a staple of science fiction, but could it actually be possible? Could we build a time machine and journey to the past or the future?
General relativity, Einstein's theory of gravity, does allow for some pretty wild possibilities, including wormholes.
Wormholes. Those are like tunnels through space-time connecting distant points in the universe, right?
Exactly. And if you could create a wormhole, you could theoretically travel vast distances in a very short amount of time. But here's the catch. To create a wormhole, you'd need matter with negative energy density.
Negative energy. That sounds like something out of Star Trek. Is that even possible?
It sounds impossible, but quantum mechanics, once again, comes to the rescue. It turns out that negative energy density is possible, at least on a very tiny scale.
Wait, really? How is that possible?
Remember those virtual particles that pop in and out of existence in empty space? Well, if you place two metal plates very close together, they can actually affect those virtual particles.
So the plates create a kind of energy imbalance.
Exactly. This is known as the Casimir effect, and it demonstrates that negative energy density is possible, at least in very specific circumstances.
So does that mean we could use the Casimir effect to create a wormhole big enough to travel through?
That's the million-dollar question. Even if we could create negative energy density on a large scale, it's not clear if we could stabilize a wormhole long enough for safe passage.
And then there are those pesky time travel paradoxes to consider, like the classic grandfather paradox. What if you went back in time and accidentally killed your own grandfather before your father was born? Would you cease to exist?
Those paradoxes are a lot of fun to think about, but they also highlight the potential problems with time travel. Hawking explored several possible solutions to these paradoxes, including the idea that history is self-consistent.
So you're saying that even if you could travel back in time, you wouldn't be able to change the past?
It's a mind-bending concept, but it might be a necessary condition for time travel to avoid those logical contradictions. Perhaps our actions are predetermined, but we just experience them as choices in our everyday lives.
So free will might be an illusion. Now, that's a thought-provoking idea. But even if time travel to the past turns out to be impossible, what about the future?
Well, traveling to the future is actually a bit more straightforward. According to Einstein's theory of relativity, time is relative. It slows down for objects moving at high speeds or experiencing strong gravitational fields.
So if you could travel at a significant fraction of the speed of light, time would slow down for you relative to someone standing still on Earth.
That's right. When you return to Earth, you would have aged less than the people who stayed behind. It's like taking a shortcut into the future.
So time travel to the future is theoretically possible, even if it's technologically challenging. That's pretty amazing.
It's one of the mind-boggling implications of Einstein's theories. Now let's zoom out from the complexities of time travel and consider the grand quest for a theory of everything.
This is the holy grail of physics, isn't it? A single theory that can explain all the forces in the universe, from the gravity that holds planets in orbit to the subatomic forces that govern the behavior of particles.
It's a huge challenge. Our current best theories, general relativity for gravity and quantum mechanics for the subatomic world, are incredibly successful in their own domains, but they're difficult to reconcile. They seem to describe different realities.
But there's some candidates for a theory of everything, right? I've heard about string theory.
String theory is a promising candidate, though it's still highly theoretical. It replaces the idea of point-like particles with tiny vibrating strings. And here's where it gets even wilder. String theory requires extraspatial dimensions beyond the three we experience in our everyday lives.
So there might be hidden dimensions all around us that we just can't perceive.
Exactly. These extra dimensions are thought to be curled up or compactified, so tiny that they're invisible to us. It's a very abstract concept, but it's one of the ways that string theory tries to unify all the forces of nature.
And how does this theory relate to everything we've talked about? The Big Bang, black holes, time?
That's what makes it so exciting. String theory could potentially provide new insights into the origin and evolution of the universe. Some string theorists believe that the Big Bang wasn't the beginning of time, but just a transition from a previous phase of the universe.
So the universe might be cyclical, expanding and contracting over unimaginable timescales.
It's a fascinating possibility that string theory opens up. But even string theory isn't a complete picture. It has its own challenges and unanswered questions.
Which makes it all the more intriguing. There's still so much we don't know about the universe, which means there's still so much to discover.
Yeah, there's always like another mystery waiting around the corner.
Right.
And speaking of mysteries, we can't forget the anthropic principle.
Oh, yeah, the anthropic principle. Remind me about that one.
It's the idea that the universe has to be a certain way, compatible, with us being here, like observers.
Right. Otherwise, we wouldn't be here to even talk about it.
Exactly. It can feel a little, egotistical.
Yeah, like humans are the center of it all.
Right. But really, at its simplest, it just says that because we exist as observers, it puts some limits on what kind of universe we can observe.
So if string theory allows for tons of different universes, each with its own laws of physics, the anthropic principle kind of narrows things down.
It does. It says, okay, out of all those universes, we happen to be in one where stars and planets can form, and there's the right kind of chemistry for life to exist.
It's like winning the cosmic lottery. But isn't this principle a bit controversial?
It is. Some scientists find it unsatisfying, like it's more of a philosophical statement than a hard scientific principle.
I could see that. We don't want to start thinking the universe was designed just for us.
Exactly. We got to be careful with that.
But Hawking seemed open to it, right? At least in a limited way.
He did. He used the weak anthropic principle, that's what it's called, to explain why we see certain things in the universe.
Like what?
Like why the thermodynamic arrow of time and the cosmological arrow of time, those both point in the same direction.
Right, because those arrows tell us about how time flows and how the universe evolves.
Yeah, and he says that intelligent life can only exist when the universe is expanding.
So we're lucky to be alive during this phase of the universe.
We are, because we can actually observe how it's changing and think about all these big questions.
It makes you wonder, what would it be like if those arrows pointed in different directions? Would time go backwards? Would we even be here?
Now, those are some seriously mind-bending questions, but I think they show how important it is to keep questioning what we think we know about the universe.
Absolutely. And speaking of questioning things, Stephen Hawking's A Brief History of Time has definitely taken us on a wild ride, right?
It has. A wild cosmic ride.
We've gone from the first models of the universe to quantum mechanics, black holes, time travel, even the search for a theory of everything.
And Hawking does it all with such brilliance and clarity. He makes these super complex ideas feel like something we can actually grasp, you know?
He really did. This deep dive, it's just a taste of these incredible ideas, but hopefully it gives you a sense of how amazing and mysterious the universe is.
And a sense of how powerful human curiosity is, you know? We're driven to explore and understand the world around us.
Absolutely. So keep looking up at the stars, keep asking those big questions, and you never know what you might discover.
That's what it's all about. It really is. And that drive to understand leads us to things like, well, you know, the anthropic principle.
Yeah,
As we were talking about earlier.
So the anthropic principle is the idea that the universe has to be compatible with the existence of observers, like us, right?
Yeah, that's the basic gist of it. Otherwise, we wouldn't be here to ponder it all.
Exactly. It feels a little, I don't know, self-centered, though.
Right. Like we're putting humans at the center of everything.
It's a bit of an ego trip for humanity, maybe.
Maybe, but at its core, it's simply acknowledging that our existence as observers, well, it kind of limits what kind of universe we can observe, you know?
Makes sense. So string theory says there could be a bunch of different universes out there,
Yeah.
each with different physical laws and stuff.
Yeah.
The anthropic principle could help narrow it down.
That's the idea. It says, hey, out of all those possible universes, we just happen to be in the one that allows for things like stars, planets, and the complex chemistry needed for life.
I got lucky.
We did. It's like winning the cosmic lottery, you know?
Right. But this principle, it's still a bit controversial, isn't it?
Oh, yeah, it is. Some scientists, they aren't totally satisfied with it. They think it's more of a philosophical idea than a solid scientific principle.
I get that. We don't want to get carried away and think the universe was made just for us.
Exactly. We got to be careful.
But Hawking, he seemed open to it, at least to a certain degree.
He did. He used, it's called the weak anthropic principle to explain why we see certain features of the universe, you know?
Like what kind of features?
Like, for instance, why the thermodynamic arrow of time and the cosmological arrow of time point in the same direction.
Okay, so those arrows are basically about how time flows and how the universe evolves, right?
Right. And Hawking, he says those conditions are only right for intelligent life during the expanding phase of the universe.
So basically we're lucky to be alive during this specific era.
We are. We get to witness how the universe is changing and, you know, think about these mind-blowing questions.
It does make you wonder, though, what if those arrows pointed in different directions? What would the universe look like?
Who knows? Would time flow backwards? Would we even exist?
Crazy to think about. But I think it shows how important it is to challenge our assumptions, to really think about how the universe works, you know?
Absolutely.
And speaking of challenging assumptions, Stephen Hawking's A Brief History of Time, it's been a wild ride, hasn't it?
It has.
We've covered so much ground. From those early models of the universe all the way to quantum mechanics, black holes, time travel, even the search for a theory of everything.
It's amazing how Hawking could explain these super complex ideas in a way that, well, that anyone could understand. He had a real knack for it.
Yeah, he did. And this deep dive, it's really just scratched the surface of these incredible concepts.
Right, just a taste.
But hopefully it gives you a sense of the beauty and mystery of the universe and, you know, just how powerful human curiosity is.
Exactly. We're driven to explore, to understand the world around us.
We are. So keep looking up at the stars, keep asking those big questions, and you never know, you might make some amazing discoveries along the way.
That's the spirit.
And that's a wrap for our deep dive into Stephen Hawking's A Brief History of Time. Until next time.